Another type of first-order differential equation that we often solve is what is called an exact equation. This video is going to answer the question, how do we solve exact equations? But before we can solve exact equations, we have to be able to identify what an equation is. And we're going to actually start identifying these exact equations by starting with the solution. Let's say the function f of xy is a solution to our differential equation, which we're going to build in just a minute. And since it's a function in two variables, I can take the partial of that function with respect to x, and we can abbreviate that f sub x. And I could also take the partial of that function with respect to y and abbreviate it f sub y. This gives rise to the differential equation f sub x dx plus f sub y dy. And what's nice about partial derivatives is if we take the partial derivative with respect to x and then y, or if we take the partial derivative with respect to y and then x, we get the same thing. So if I suspect this differential equation is an exact equation, I can start with the dx part and take the partial with respect to y, and I can take the partial with respect to y and take its derivative with respect to x. And if those are both equal, we have an exact equation. From there, we can look at solving this exact equation by undoing the partial derivatives on both halves. We can take the integral of the partial with respect to x dx, and that's going to give us the original function plus a constant in terms of y. And we can integrate the partial with respect to y dy, and that'll give me the original function plus some function h of x. And if I combine the parts of both of these results together, we end up with f of xy, the solution. And it has to be equal to a constant. That's where we account for the integrating constant that comes from integrating. But this process builds quite nicely the function f of xy that is the original solution to this first-ordered exact differential equation. Let's mark that it is the solution, and then take a look at some examples where we work out this process. For our examples, we're going to start with 2xy dx plus x squared minus 1 dy equals 0. And since it's almost set up in that exact form, in fact, it's exactly set up in the correct format, I first need to verify, is it exact? The dx means that part's already done the partial with respect to x, so I'm going to do the other variable and take the partial with respect to y. And when I do that, I end up with 2x. The dy implies that we've already done the partial with respect to y, so I'm going to do the partial with respect to x, which is also 2x. They are the same, so that tells me this is an exact differential equation, and we can use the exact process to solve. We're going to undo the integral of 2xy dx, and we're going to undo the integral x squared minus 1 dy to see what we end up with. When we integrate with respect to x, treating y as a constant, we end up with x squared y. When we integrate the second integral with respect to y, we get x squared y minus y. To build our solution, then, we take the union of the terms. In other words, we've got an x squared y which is already accounted for over here. We do not list it twice, only once for each term. But then we've also got this minus y. And we set that equal to our constant to get our solution for the differential equation. Now, if it's nice and easy to solve for y, we like to do that as well. So let's factor out a y to get x squared minus 1 is equal to a constant. And then y is equal to the constant divided by x squared minus 1. And we've solved our differential equation. Let's do one more example. Let's try one that's a little more exciting. Let's do e to the 2y minus y cosine of xy dx plus 2x e to the 2y minus x cosine of xy plus 2y dy equals 0. Now, because of the format, again, I suspect it might be an exact equation. Because we've got our dx, we know I need to take the partial with respect to y. Be careful here, this partial is a little bit trickier to take. The first part's straightforward. E to the 2y becomes 2e to the 2y. Minus, we've actually got a product here, so we need to use the product rule. The derivative of y is 1 times the second, which is the cosine of xy. And then plus, but distributing the negative through, y times the derivative of cosine, which is negative sine of xy, times the derivative of the inside, using the chain rule, is just x when we're taking the derivative with respect to y. On the right side, we'll take the partial with respect to x, because we've already done the y. Partial with respect to x is equal to 2e to the 2y minus, again, we're going to use the chain rule. The derivative of x is 1 times the cosine of xy. Distributing the negative through, except x is a constant now. The derivative of cosine is negative sine xy. And then we multiply by the derivative of the inside, which is just y. And 2y is a constant in terms of x, so its derivative is 0. And sure enough, both of these are exactly the same. So we verified that we do have an exact equation. In order to solve the exact equation, we're going to integrate both parts, e to the 2y minus y cosine of xy dx. And we'll integrate 2x e to the 2y minus x cosine of xy plus 2y dy, treating the opposite variable as a constant. As we integrate with respect to x, the integral of e to the 2y is e to the 2y times x, because that's just a constant, minus, y is a constant, the antiderivative of cosine is sine of xy, and then using a substitution, we're going to have to also divide by y, which means y divided by y becomes just 1. On the other side, dy, so 2x is a constant. E to the 2y's integral is e to the 2y divided by 2, so those 2's are going to reduce out. Minus, x is a constant. The antiderivative of cosine is the sine of xy. But then we're going to have to divide by x, which makes the x over x go away, plus 2y's antiderivative is y squared. Now that we have all the pieces, we just have to put them together to make our solution. We've got an x e to the 2y on both. We've got a negative sine of xy on both. Again, remember, we don't need to repeat it just one time. And then we've also got a plus y squared. We're taking all the pieces and putting them together without repeating pieces. And that's going to equal our constant, and we've solved our exact equation. The hardest part of these is identifying them as an exact equation, because once you have, you just integrate and take the union of the terms equals your constant, and you're done. So take a look at practicing some of these on the homework assignment, and good luck to you as you work on them.